So, um, just tell me really a little bit about your background and how you came to be involved in the interneting experiment.
Okay. I came to UCLA in 1970 as a graduate student in the Department of Computer Science. I don't think at that time networking was on my mind, really. Was getting graduate degrees like a master's and hopefully a PhD. And eventually, my first course was with Len Kleinrock. I took his queuing theory course and got to know some of his students. And they were already working on problems related to computer networking. In fact, the first imp of the ARPANET was already placed at UCLA a year before I got there, so September 1969. So activity on the ARPANET was already taking place. So eventually, after having taken the courses that I needed to take, etc., 2 years later, it became time for me to start doing research. And problems I started looking at had to do with distributed processing and communications optimization, but I couldn't find anything that people had not done before, and probably there could be, but a thesis that I had started reading about on this subject seems to have studied many of the problems that I could think of. And in December 1972, my advisor, Professor Len Kleinrock, I will refer to him as Len from now on, asked me if I would come with him to a meeting at SRI on a new project. In a sense, the ARPANET was already going on. Many nodes were already in place. There was, in a sense, an operational network. SATNet had already started, and that was the very first meeting to establish the packet radio network working group. Yes, in December 1972.
Right.
I came to this meeting, and I was really fortunate as a graduate student looking for some research work to do. Be exposed to this new project. It was to be defined, but basically it was understood that the goal is to use radio and for communication and packet switching, and to do something beyond what the Aloha system did, which is a one-hop system from terminals to a central computer. In which case it required that we look at extending the range of any particular radio unit so that we have connectivity over a wider area than what radio propagation would have allowed. Okay, well, I could tell you, since that moment, I attended every working group meeting until about 1987, having seen even a change in the directors of this program or managers in this program, from Larry Roberts, who was directing it in the first maybe year or so, then Bob Kahn, Vint Cerf, Barry Liner, and in a sense until 87, when I stopped getting involved in it, in a sense, even though it was going on. For ARPA, this is a project that had a lifetime much longer than any other project they had, and in a sense, longer than what would have been expected as a lifetime for a project before having to transfer it to, let's say, the users, which in this case would have been the military. And therefore, its name has changed over time from packet radio network to SURAN, or survivable radio network, to later on global mobile communication, or GLOMO, the GLOMO network, or GLOMO research, and later on ad hoc networks, So this is a program that has gone on for quite some time. Traditionally, UCLA, whether in the development of the ARPANET or SATNet or packet radio, had basically two major roles. One of them is the theory, as Don was saying a little earlier. Obviously, Len had done lots of work on design of networks, packet switch networks. Also, there was work going on in slotted aloha and understanding its behavior and performance evaluation. But the second, and the same happened therefore in packet radio as well. The second role is that as UCLA was the network measurement center. You know, BBN was the network control center for the ARPANET, SRI, among other things, the network information center, and you had UCLA, the network measurement center. So there was kind of a division of responsibilities among the various contractors and players. And we therefore played also a role in that respect. So for packet radio, therefore, we did protocol development and analysis, as Don was saying, channel access protocols, and two, network measurement and simulation. And I could tell you a little more about these in more detail, if you wish.
I will.
Yep.
But you were working then with, I mean, you were one of the few places other than DARPA that sort of saw all the players in this.
In a sense, yes. There were times questions as to why on earth are we here? And I would sort of say, you know, I remember I was in meetings before where, because of some limitations, we decided to take this route. I could give you examples. Okay. Well, the radio units were very limited compared to what you would consider today. You have in a laptop or in a cell phone, obviously. Many times there was mention of the fact that a microprocessor, 16-bit microprocessor called the National IMP16, I think, the National 16-bit microprocessor.
Made by?
National Semiconductor.
Okay.
Yeah, I think it was called the National IMP16, IMP-16. So
yeah,
besides it being only 16-bit processor, we were very limited in memory. I mean, there were 4 KB of RAM and 1 KB of ROM to contain not just packet buffer, but all the protocols that were needed to run this packet radio unit. And a packet radio unit was at the same time the interface for a user's terminal, as well as a store and forward router, finding the right route to reach the destination, while all these nodes could be mobile. Okay. So therefore, one of the kind of tension that always existed had to do with what functionality you want in the protocol, but what could also fit
sure.
on this memory.
So people would write and rewrite to pare it down?
Or would say, gosh, you know, while this may sound like it's a good thing to do, we're not going to want to do it because it takes so many more words of memory to implement the software.
And this is all machine language then?
Assembly language.
Yeah.
Absolutely. Yeah. Okay.
You're squeezing every last.
Exactly. And Collins Radio was responsible for building these radios, was also the hardware, that is, and the RF section and all that, was also responsible for writing the software to go on these radios. Okay. So it's possible that they didn't develop the protocols themselves, but they had to write the software for it. And then they delivered a unit, hardware and software, that SRI would put into a test bed and make work with other radio units. Of course, there could have been some testing done also at Collins Radio or what have you, but what I'm saying, that's what Don was kind of referring to, that somebody else would have done pieces of equipment or pieces of software, and they had to assemble them together into a network and make sure they work together.
Yeah.
Okay. As a matter of fact, since we were, maybe I'm stepping a little bit ahead, later on as Network Measurement Center and involved in this project, one proposal we had to DARPA, and I had write the section on measurement, we had a number of objectives to meet in seeing that, number one, the radios are working properly and performing well from an efficiency point of view, from a network performance point of view. So there was a series of in a sense, measurement objectives, each specifying what particular configuration the testbed had to take and what particular measurements would be collected in order to be analyzed offline then and be able to assess then the performance of such working units. And I remember that there were times when Collins Radio would object to having extra instructions having to be put there for the purpose of measurements. And one of the fellows by the name of Stan Lieberson, who worked at UCLA with me on this project and was good in assembly language programming, would go and learn the assembly language that was used, write the instructions that would be needed, and count the number of extra words that would be required in order to collect these measurements. And we go to Collins and say, look, it's not so much. It sounds like it's a lot, but that would be very helpful if we could have these embedded into the.
And so you were
software.
dealing directly with them, not through SRI. Right?
Well, yes. In fact, we have, our proposal was to ARPA, and then we say here are the things that we think should be embedded in the software for doing the measurements and collecting relevant data. And then, we passed that on. And of course, there was objection. And one time we go to BobCon, and there was a meeting at Rockwell International, and we were told, no, we cannot put these things in. And we go to Bob, and Bob says, measurements are very important. So if I don't do this, they'll lose their contract with me. And then the next thing is I knew that, yes, they were going to be implemented in. So in any case, I did not, let me put it this way. I started in 72, as I mentioned to you. And went on, in 74, I graduated, got the PhD. And I'll tell you a little bit about the kind of work I did as a graduate student in that case. And then stayed at UCLA for 4 more years, principally working on this project. So I was a full-time, research associate
Postdoc,
or engineer, postdoc, but I had responsibilities more than a postdoc. Postdoc is almost like a research assistant that stayed beyond the PhD.
But you were not
I was
you were
hired.
not an assistant professor, were you?
No. In fact, UCLA had a rule not to hire its own graduates. In fact, it's common in many places, unless you have gone somewhere else for several years and come back fresh, new, different from what you were as a student there, to avoid too much kind of redundancy.
Incestuous.
Exactly. I mean, isn't this field already covered by the professor you worked with? Why would you be there, etc. And since I stayed right after, so I could not have a faculty position. But I did, with permission from ARPA or taking some time off, percentage of time off, I did teach courses during those 4 years, regular courses in the department. Well, in that case, they were more the undergraduate courses in computer science. Therefore, I taught data structures and automata theory. These are the 2 principal courses I remember having taught to fill in instead of having, in some cases, lecturers from outside doing these courses. I was in the department, so I could do these.
And how many people, you were working directly with Len, how many people were?
Well, Len and I were principally the people involved in this project, but I can add a few more people and staff that came on board to help us in various ways. Because depending on when in the course of this project we had need for extra people. So as a graduate student and going to all these meetings, we at the beginning we didn't have like a particular specific role to play, like we will be working on routing protocols or channel access protocols. So we were kind of free to look for what could be the right piece of work to do. And well, there were quite a few contractors involved, some also in architecture and protocols. For example, Network Analysis Corporation may not have been mentioned here, was a major...
It has. No.
It has been, yeah, Howie Frank and some other people from his company then. He used to be at Berkeley.
It was mentioned, but more that I remember the name.
Yeah.
Not much about them.
He was an ex-professor of Berkeley, but he formed Network Analysis Corporation, NAC, and set it up in the New York area in Long Island. And I remember having visited there because one time we had one of the meetings there, one of those working meetings. And one fellow by the name of Israel Gitman was very involved in this project. And they had their own ideas about how to do routing or labeling the radio units so as to have a coherent network where the units know each other or the stations know who the units are and things of that sort. And while I had started looking at problems of this sort, eventually it became clear that the channel access issue was quite important. Obviously, UCLA was doing work on Aloha, slotted Aloha, and analysis thereof. And at one of the meetings that took place in Dallas, Norm Abramson was also present. And that's when he mentioned the idea of that one of his technicians, Dave Wax, had brought up when they would use repeaters to extend the range of the Aloha system to other islands. Maybe the two repeaters sharing the same microwave link could listen to each other before transmitting. In other words, check that the carrier is idle, there is no carrier as opposed to transmit, even though that could be carrier. So as long as the receiver is detecting carrier, you wouldn't switch to transmit and transmit. Rather, you would be receiving what the other would be transmitting. So that was a simple kind of idea.
And you came up with a name then?
Yeah, well, what happened is that, on the way back from that meeting, Len and I were together on that trip, and we started thinking about what this could look like. And eventually, indeed, that happened sometime in the winter quarter that followed that first meeting, December 72, so early on in a sense. And I started working on this subject. And, came up with a protocol I called One Persistent. And we refer to it as actually auto-slotted Aloha, so we didn't have the name. And then looked at variants, because eventually, as part of a working group, for thinking of channel access protocol like Aloha, I mean, there could be input from many people. I do have to cite quite a few people that influenced me also in the work, like Dick Binder himself, Stan Fralick at SRI. But I was doing good work, good analysis to the point, and made it a coherent theory to the point that I benefited from their input, but we became almost the owners of this matter. And at one time it became...
But the name...
Well, that's what I'm coming to.
Yeah.
Came a point in time it became important for us to publish this work. The very first paper we published, we called it, as I said, auto-slotted Aloha, because it was still thought of as Aloha. In fact, without going into the details, if you use one persistent, you persist on transmitting right after the channel becomes idle, given that you have seen that somebody else was transmitting, from that point on, it would start looking like slotted Aloha, but where the slot boundaries were not defined a priori, and you were not in sync with a common clock, and so on and so forth. And it gave a better performance, like 55%, as opposed to 36% in slotted Aloha, or 18% with pure Aloha.
Yeah.
But then the idea that you didn't have to persist until the end of of a transmission and transmit with probability 1, because in that case, if 2 or more happen to be waiting for this end of carrier and transmit at the same time, they certainly will collide. So I start thinking of prioritizing a little bit when they transmit. So in other words, you flip a coin, instead of the probability 1, let the probability be P. So we call it the P persistence. Yes. And you flip a coin.
But it becomes randomizing. Not
yeah, you
prioritizing.
randomize when you can transmit. Yeah. Okay. So you flip a coin and you say, if it's head, I transmit. If it's tail, I wait and see if somebody else has transmitted. So the question then, how long do you wait? You wait a mini slot, the appropriate time for somebody else's transmission to have reached you, because then you have feedback as to whether or not somebody else has transmitted. So it was on the order of a round trip time. Okay. And then you repeat. If nobody has transmitted, then you repeat, because others could be in the same situation. Finding that nobody has transmitted, would still flip the coin and try to transmit. And then the idea, I think Stan Fralick came up with, if I find that the channel is busy, I just go away, try again later, reschedule immediately. And then I start realizing that all these are very much related to each other in the way that I have talked about it. One persistent, non-persistent, or P-persistent. And it's a family, but that's a continuum in a sense, depending on what probability you use and whether you go away, which is a rescheduling. It's like saying...
Which is a...
It's a rescheduling to some later point in time. Okay. So these became really the things that we started working on, and then developed the theory, the analysis thereof, and compared them and all that. But I do want to stress the fact that other people's thinking helped a lot. We were all in very good terms working all together. And but I marshaled this and doing all the analysis and simulation thereof. And then when it became time to, kind of write this paper and send it for publication, I remember going to Len's office and say, but what name do we give it? It's no longer just auto-slotted aloha. That was the wrong thing. And we could do much better, get better results with P-persistent and non-persistent. And I would tell him, I just was reading a paper that talks about time division multiple access, frequency division multiple access, code division multiple access. Why don't we call it carrier sense multiple access? And the term CSMA. He was not very happy about that, wanting something that's more catchy. He says, how about charisma or something like that? I said, I'm more conservative, I guess. I like CSMA because it rhymes with all the others. And the paper, the journal paper that went out, and eventually appeared in December 1975. Maybe we had submitted it a year and a half before that. Bear the name, Carrier Sense Multiple Access, or CSMA. Obviously, another interesting point is that Xerox PARC was somewhat involved also in this packet radio project, and Bob Metcalf in particular.
It's true. The SRI people didn't... I heard a little bit about that from...
In the early days, let's put it this way. For example, I do recall very well, these are some of the anecdotes, when Larry Roberts was still coming to the meetings or heading that particular project, he would be talking about the goals, right? And, there will be a jeep or a tank, and you would be able to communicate with the other, and Bob Metcalf, who never liked necessarily the military applications, and even though they were needed to sponsor such projects, and he would say, you mean the ambulance? You mean the fire truck?
Artillery piece.
Yeah, thinking more of it as a civilian application rather than military application. And in fact, it made sense in the sense that even though that's who the client is and would want this developer, we can justify a need for, but the applications go way beyond. And he was at the meeting when carrier sensing between the two repeaters in the University of, this Aloha system came up. But his interest and his goals at Xerox was to connect the Altos, those personal computers that were precursors to what we know the PC is, as we were saying earlier, to connect them in his building. And he had spent time at the University of Hawaii working on packet broadcasting and the Aloha system. And and therefore his idea was to sort of do something like that, but inside a building, communication via radio was not necessarily very good.
Oh, but when the idea of doing it inside a cable
Exactly.
came later? Or he thought about it first?
No, he thought about it.
Right,
He said,
but he
"Let me
wasn't
use-"
thinking of a radio network. He went straight to the cable.
Absolutely.
Okay.
But no, he was, of course, he was at the University of Hawaii
Yeah,
before.
sure.
I don't know for how long, but knowing about Aloha and packet broadcasting. Then he was part of this radio
Right.
project and this particular meeting when Norm Everson talked about carrier sensing. So knowing that it was better for him to use a cable.
A lot faster.
But in the same way you would have used radio and called it the ether, he did carrier sense multiple access on it, in a sense, carrier sensing to prevent collisions, but added the collision detection.
Right.
Which
So
you
it
could
would
have on a cable,
actively-
but you could not have in radio because radios are half duplex. You cannot have your receiver on while your
Right.
transmitter on to know that you are being collided with.
So that increases the throughput
That
enormously.
further, exactly, and introduced
From
the
what percent? A lot.
Let me put it this way. As I told you, one persistent, where you persist on transmitting at the end of a transmission because it blocked you or whatever, can get you 55%. Well, you didn't want to do it because in radio, there's no way you're finding out if you're colliding with somebody else, but you would go the entire transmission and therefore waste channel time for the entire transmission. With collision detection, it pays to try. Because immediately you
There's no
see if
cost.
another person was also doing the same, and you will abort the ongoing transmission and then not waste the entire time. So you could again recover the high kind of efficiency of non-persistent or adjusting P-persistent, knowing that a collision will hurt you a lot without needing to do that. So therefore the Ethernet protocol that he has is a one persistent CSMA with collision detection.
And he dropped out of that group, what, 74 or something?
Well,
like
because,
that?
building the Ethernet was more important for him. But the radio unit, set up at Xerox PARC was one of the Bay Area test bed.
So in that period, you remember going to Xerox PARC and meeting a number of those people?
No, as a matter of fact, the way things, I learned about him working on that at Xerox PARC was by receiving a visitor. Len Kleinrock was receiving visitors all the time, and here came a visitor. I don't recall the name, unfortunately, but from the RAND Corporation. And Len talks to them a little bit, and they say, talk to my students and talk to Fouad Tobagi. He would come to talk to me. So I was describing to him the carrier sense multiple access aspect and the analysis thereof, and here are some simulation results, and so on and so forth. And then he would say, I was visiting Xerox PARC, Bob Metcalf. I say, yes, I was visiting Xerox PARC just last week, and they are doing something of this sort. Carrier sensing on the cable. On the cable, for me, was not interesting. I'm a packet radio person, right? And then he tells me, on top of that, they have the ability to detect collisions. So that's what actually made me a little bit nervous, Here is all this work, and we haven't published it. So I don't want to know that eventually publications come out from elsewhere before ours. That's when I jumped into Len's office, and I said, we need to send this right away. He says, sure, because I had been writing everything. As I go to packet radio working groups, I would write notes and then submit them and describe them to the rest of the group. So a lot of things were already written. And so that's when I said, maybe we can call it CSMA, and let's go for it, and wrote the paper to submit it. That's why, in a sense, our publication of 1975 in the Transactions on Communications preceded anything that came out from Xerox PARC and Bob Metcalf on the Ethernet.
But he was not even allowed, probably, to publish.
Exactly, because they were patenting. Okay, so with the patent being in view, patenting being in view.
But you didn't know that, of course.
No, I did not know,
Yeah.
except from this fellow who came to visit me and say, they are doing something similar
Right.
to this. And then I said, let's get the papers out. And So I have worked on it. We submitted it while I was still a graduate student. My thesis was not done yet. Yeah. So this is work that came out from the packet radio that is still living today. Whether today, the packet radio network exists or not, as we had it then, is not important. But carrier sense multiple access, and thanks to Bob Metcalf, was part of Ethernet. So all these years, and you might say today, Ethernet and local area networks are more switched than based on sharing media, right? The medium, as in carrier sense multiple access. And therefore, maybe it's not needed except between two nodes that are sharing and have to plex even link. Now it's mostly point-to-point links, right? Between in Wi-Fi,
sure,
you need it. And the standard 802.11 is all carrier sense multiple access, maybe with some variations like collision avoidance to overcome the hidden node terminal, among other things. But that's exactly what we could. That's what we had also in the packet radio network.
And how about cell phone networks? Do they?
No, because so far, at least, cell phone networks have used circuit switching. No matter whether it's DDMA or DMA.
Even for data, really?
Well, for data, but then.
No, but like GPRS or something like that.
Right. I do not know in GPRS what they do on the radio access network, but I know that, in fact, I should know, but I'm not sure it's clear in my mind right now, because I looked more at their mobility management for GPRS to get things to track the mobile users. I can't
Don't worry
recall very well now. Whether it's still circuit oriented or not, I do not know. But one thing I can say is that radio access networks of the type that's defined in Wi-Fi is already used, integrated into the system. So at least for that, for hotspots, it makes sense. Even for packet for voice communication. I mean,
sure.
And sooner or later, you're going to see everything become of this nature and circuit switching, in a sense, disappearing. So, okay.
And we've got a few more minutes.
Right.
But tell me whether, well, first of all, kind of up to you whether you want to wrap up now or should we make this part one of something and meet another time? But,
maybe, I don't know if it necessarily merit another session. The only things I would like to say that UCLA also spend a lot of time on. So this is like work on channel access protocols, which became really major development in the field of multiple access that remain extremely strong and still is today. One thing that came out of the packet radio project also is the concept of layering the protocols. It was not so important in the ARPANET to think of it that way because let me say, comparatively, the functions were relatively simple. Okay, even though today we know that they can be certainly mapped and they are mapped to the layered concept and everything, and the ISO layering in a sense. But with packet radio, it was really important to think of that. You had the physical layer and how we communicate over a wireless channel sending digital bits. Okay, whether you use spread spectrum or not, and whether you do you detect carrier or not. The second point we did then is, or we had to identify separately, was channel access protocols. We didn't call them media access control sublayer as we call it today. When LANs became standardized, they gave it the name of media access control. We called it channel access protocol. And I remember at one meeting that we had at DARPA, I volunteered to go on the board to write down these layers, since the discussion became very confusing to me, each one talking about the different functions. And then I remember writing, physical or the wireless channel protocol, then channel access protocol, and above it came the packet radio unit to station protocol that Don was mentioning. Given the limited capacity or capability of the radio units, we counted a lot on like a base station to provide some intelligence, either for routing or for labeling these radio units. And therefore, there was a protocol for radio units to talk to the station to say, I am alive, I want to be labeled so that I'm part of the network, etc. And then above that, routing so that you know how to go from one packet radio unit to another. So the layering concept came before I ever got exposed to it in the context of ISO or OSI and all that. And so these are important.
It wasn't formally described that
No,
way.
we didn't. But on the board, we were tracing lines like these to sort of say this comes on top of that. You know how to transmit bits. Now you know you have to decide when to transmit. And that's media access control. And then you have to communicate with the station so that you can be known and identified. You had to have the other in order to be able to transmit or access, but then in order to be identified. And before, you could not be a router, either relaying traffic for other users or be the source or the destination if you were not labeled and understood. So above it will come then routing.
Yeah.
So we dealt with all of these things.
Effectively, yeah.
And in terms of later activities, as we were the network measurement center and all that, we had staff, in fact. Well, in the earlier days, maybe some undergraduate helped me with the programming or getting my simulations run on the computer, as you have seen here. We had to go through card readers and wait for our job. So as a PhD student, I had maybe better use of my time than doing that. So I had great help in that case from students hired on the project, but to assist me in these things. But later on, we had, as I said, the measurement fellow, Stan Lieberson, and defining exactly how we would collect data in these PRUs. We also established a program for doing a simulation of a multi-hop packet radio network in order to understand how higher layer protocols would behave. And these were very complex tasks, because in those days we couldn't, even today we have lots of work going on in terms of simulation of what we call ad hoc networks. But in those days, it was not easy to come up with, a simulation that would run fast enough to give us the right results. And after I left UCLA to come to Stanford, where I am now on the faculty, and since 1978, this project continued directed by other people. And eventually that whole activity of simulation, etc., got transferred to SRI because no one at UCLA was. Yeah, the fellow who followed me and continued the measurement and mostly the simulation, if I'm not mistaken, that part of the project got transferred to SRI. Yeah.
And it exists today or not?
Oh, no, I don't believe so. But a lot of other efforts in writing simulations for these networks has taken place, again at UCLA, I have to say. And one of the programs that came out from there is called GLOMO Sim, for Global Mobile Communication Simulator, which has been turned into a product by some of the members of the UCLA Computer Science Department. It's known as QualNet, and apparently there is good use of it in the military and some universities for simulating ad hoc networks. Yeah.
And the, in 77,
Yes.
how much of, if any, impression did you even know what was going on?
Oh, of course.
Of course.
I mean, let me put it this way. I never got too interested in what we called the implementation working group was doing. That is the Packet Radio Network Working Group. And there was the so-called implementation working group, or today I heard a reference to it made as the TCP working group. Okay, for us was the implementation because they are implementing gateways, implementing the terminal access unit or the interface unit, right? The terminal interface, the TIU. Now, maybe one point could be interesting. So what is this terminal? In those days, you have a terminal as a user, a keyboard with a screen. You see what you have typed. And therefore, to be part of a network, given that you only have a dumb terminal, You had a box behind it, which was a computer
Right.
that became the terminal interface
right.
unit.
Like the terminal imps.
But today, the terminal interface unit and everything it did is an integral part of any laptop or whatever, right? So always there was an interface unit because you didn't program dumb terminals.
Right.
Nor did you have a computer as a personal computer. So it was a box without the screen or anything.
But in
Yeah.
77, though, in November, you knew what SRI was doing with some of these demos?
I was at all the meetings. I drove in the van too. I
Right.
rode in the van rather with Bob Kahn. At one, to do interneting, you needed two networks.
Yeah.
First, there was the ARPANET. SATNet, as was said yesterday in the on the panel, BBN was thinking of it more as you put modems. It's an A channel, so it was like a link as opposed to a
Yeah.
network, right?
Right.
When you think of it, like let's say you are extending it only to UCL in London, it was not a network in a sense, right? But obviously, if you think of multiple Earth stations and they are using reservation, Aloha, whatever, it's like a LAN, but it's a satellite network. It's
Yeah.
like a LAN segment. Here it's a satellite network segment with multiple stations sharing that segment. So by placing a gateway between
Sure.
this one and the other one to make up for the differences in characteristics, long propagation time
Yeah.
versus short propagation time, it made it a separate network. But before, for packet radio to be connected, it could be a standalone network, but to be connected to the ARPANET, you had internetworking that was required to begin with.